Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper trending on X, published on July 29th, 2025. So, just 2 days ago. This paper presents some really fascinating, tentative evidence that the interstellar object 3I Atlas was active even before its discovery, at a huge distance of about 6.4 astronomical units from the Sun. The paper is titled, Precovery Observations of 3I Atlas from TESS suggests possible distant activity. And as we'll see, the methods they use to find this faint object in old data are pretty clever. The team analyzed archival data from NASA's TESS satellite, finding some of the earliest images ever taken of this third known interstellar visitor to our solar system. Alright, and as I mentioned, this is definitely getting some attention on X. The conversation is quite lively, with one account, Skywatch Signal, framing the object as an interstellar visitor that refuses to behave like a comet. This has kicked off a bit of a debate, with some users asking for scientific backing, while others defend more speculative theories. That initial post has strong engagement, with over 400 likes, and interestingly, others in the thread are pointing directly to the research we're discussing as another piece of the puzzle. So, to really understand the science behind those claims, let's dig into the raw data the researchers started with. This figure shows the TESS full-frame images, which are essentially the complete, unprocessed pictures from two different camera sensors. These sensors are what we call charge-coupled devices, or CCDs. The top panels show the wide view, and you can see how one area is much brighter and more crowded with stars. The tiny orange boxes highlight where 3I Atlas was located, and in the zoomed-in views below, you can see it's completely invisible, which really highlights the challenge here. Building on that challenge, this next plot shows just how much noise the team had to deal with. This graph plots the overall brightness of each image over time. Those huge U-shaped curves are what the authors call orbital ramps. Basically, it's contamination from scattered light from Earth that creates massive swings in brightness. These are a type of systematic, which are errors that come from the instrument itself, not the object they're trying to see. The yellow sections highlight data that was just too messy to use. So before they could find 3I Atlas, they had to remove all this noise. So after removing all that noise, here is the result. These are what the authors call deep stack images, created by layering and aligning thousands of those noisy frames right on top of each other. And it worked. You can now see 3I Atlas as the bright yellow spot inside the red circles on both camera views. They achieved a statistically significant detection, specifically 3.7 sigma and 4.1 sigma. In astronomy, sigma is a measure of how confident we are in a signal, and these values mean it's very likely a real detection, not just random noise. This table then details the specifics of those detections. It breaks down the observations by the two different camera and CCD pairings, showing the exact dates from early May to early June 2025. It also lists two key measurements, the object's heliocentric distance, which is its distance from the Sun, and its geocentric distance, its distance from Earth. What's crucial here is that the heliocentric distance was huge, starting at about 6.4 astronomical units, which is over 6 times the distance from the Earth to the Sun. This detail is the foundation for the paper's argument. Okay, so after detecting the object, the next logical step was to see if they could measure its spin. This figure shows their attempt using a Lomskardal periodogram, which is a special tool for finding repeating patterns, like a rotation period, in brightness data. The orange line for 3I Atlas shows a potential signal around 28 hours, but the yellow line, which comes from a nearby background pixel, shows a similar peak. This told the researchers the signal was likely just instrument noise, meaning they couldn't determine the object's true rotation period. Moving to the main finding, this next plot reveals something crucial about the object's activity. It charts the absolute visual magnitude, or HV, which is a standardized measure of an object's intrinsic brightness. The key thing to remember is that a lower HV number means a brighter object. The orange points are the new measurements from this study, while the black points are later observations of 3I Atlas. What's striking is that the brightness from these early observations is consistent with the later ones, suggesting 3I Atlas was already active, producing a coma of dust and gas. So, to wrap up, these early observations suggest 3I Atlas was active much farther from the Sun than expected. This hints its activity is driven by hypervolatiles, things like frozen carbon monoxide. It's a fantastic use of archival data to learn about these interstellar visitors. That's it for this episode.